A very good morning to respected teachers. This is Harshita of 12th B, and today the topic I have chosen for my presentation is solution. So let's move on to this presentation. Whenever we hear this word solution, a question strikes into our mind that what this solution is. So solution is homogeneous mixture of chemically non-reactive substances whose composition is within a limit. Means we can add solute to solvent within a limit. After it, it will not be able to dissolve. What is this homogeneous mixture? A homogeneous mixture is a mixture in which the composition is uniform throughout. You will not be able to identify the boundaries between the solute and the solvent. For example, in I have taken sugar as solute and water as solvent, and the obtaining resulting mixture is a solution. I can say it as a solution because here I am not able to find any particle of sugar. I am not able to identify where the particle of sugar present and where the water. It is all uniform throughout. And when it comes to sand into water, it is not a solution because I will be able to see the particles at the bottom of the container floating into the water, and that's not a solution because solution is a homogeneous mixture, not a heterogeneous mixture. This is a heterogeneous mixture and this is a homogeneous mixture, and solution is a homogeneous mixture. Components of solution is solute and solvent. As you know, solute is present in less amount, solvent is present in more amount. Now, a point to be noted is may or may not have the same phase as solution, but solvent always have the same phase as solution because solvent is present in more amount and solute is present in less amount. Therefore, the state will always depend upon the solvent, but in case of solute, it may or may not depend. Next is types of solutions. So when it comes to a solvent, which is a gas, it is a gaseous solution. When the solvent is liquid, it is a liquid solution. When the solvent is solid, it is a solid solution. When in gaseous solution, the solute is a gas. We can take example of air and oxygen, nitrogen, hydrogen, CO2. We can take example of all these gases. As we are not able to uniquely identify where the oxygen is present, where the particles of nitrogen gas is present, it's all uniform throughout. When it comes to liquid and gas, humid oxygen, or we can say we should take H2O, in air. Now here H2O is in vapor form, in water vapor form. Next is solid in gas, that is camphor in nitrogen gas. When it comes to liquid solution, if the solute is gas, we can take example of CO2 dissolved in water or O2 dissolved in water. When liquid in liquid, we can take ethanol dissolved in water. Now basically ethanol is an alcohol. When it is solid in liquid, we can take salt water or sugary water. Means the sugar is solute here. When it comes to solid solution, if the solute is gas and solvent will always be solid. When the solute is a gas, when we add hydrogen or any other gas to these solids, that is palladium, platinum, nickel. Now these are known as catalysts. What they do, they increase the speed of the reaction. Actually, they absorb the particles of the gas onto their surface, and hence the number of particles participating in the reaction gets less, and hence the speed of the reaction increases. That is why catalysts are used in reactions for a faster result. When it is liquid in solid, amalgam of potassium. When it is solid in solid, gold alloy or any metal alloy. Next is concentration time. So concentration is amount of solute present in a solvent. We can calculate it in following ways. First one is presentation percentage by mass, volume percentage, mass volume percentage. Now for these three we have formulas: mass of solute upon mass of solution into 100, volume, mass volume. Here in these formulas, volume is always taken in ml and mass is taken in grams. Next is parts per million, mass of solute upon mass of solution into 10 raised to the power 6. Mole fraction, you can calculate the mole fraction of any of the component of the solution. For example, I have to calculate the mole fraction of A, that is solute, that is solvent, let's say that is solvent, and upon the moles of solvent upon moles of the solution. This is how you can calculate the mole fraction of any component. Next is molarity and molality. Now molarity is not considered to be very good option when it comes in front of molality, because molarity depends upon temperature but molality not. Now molarity, why molarity depends upon temperature? Because here in its formula if there is volume, molarity depends upon volume and volume depends upon temperature. So molarity indirectly depends upon temperature, but molality is having mass at the place of volume, and mass doesn't depend upon temperature. So that's why if the temperature will increase, the molarity can be variable, but molality is not. Next is normality. Normality is equal to equivalent of solute upon volume in liters. Next we have solubility. Solubility of solids in liquid. Now amount of, what is this? Amount of solute in grams that can be dissolved in 100 gram solvent to form saturated solution at a particular temperature. Now factors affecting this solubility are nature, temperature. Nature of solute and solvent means what type of substances they are, whether they are containing polar molecules, they are polar substances, or they are non-polar. If they are polar, polar dissolves in polar and non-polar dissolves in non-polar, but polar is not soluble in non-polar. Here you can see when I take the example of NaCl and H2O, it is polar and polar, so it is solvent, the soluble. Solubility is there because both of these are polar substances. But when it comes to NaCl and benzene, both of them are having different nature. One is polar, one is non-polar. So it will not dissolve in benzene. It will not be soluble in benzene. Next factor is temperature. For some substances, with temperature, the solubility, with increase in temperature, the solubility also increases. But for some, it decreases with increase in temperature. For substances whose solubility is directly proportional to temperature means when the temperature increases, the solubility also increases. The dissolution is endothermic. Now, endothermic means the energy is required for the reaction. For some substances to react, energy is required for their reaction, and they are getting that energy, so they are able to react properly. But for some of them, it is exothermic. The dissolution is exothermic, so they don't want any energy. They are willing to release energy, but they are getting energy when we are increasing the temperature, so it's not in their favor, therefore their solubility decreases. It decreases the speed of their reaction, therefore the solubility also decreases with increase in temperature. Their example is KNO3, KCl, NaCl, and for substances whose solubility is inversely proportional to temperature, Na2CO3 dot H2, Cl2SO42. Now third type is also there, substances showing irregular trend of solubility. Once with increase in temperature, their solubility will increase, but then with increase in temperature, their solubility will decrease. Reaching a certain point, this first of all their solubility will increase with increase in temperature, but reaching a certain point, their solubility will decrease. Like here in this graph, we are seeing three of the options, A, B or C, three other possibilities. Here it is solubility and here it is temperature. So A type of substances are when the dissolution is endothermic and solubility is directly proportional to temperature. We are increasing the temperature and hence the solubility increases. Here in B type of substances, we are increasing the temperature, the solubility is decreasing. Solubility is decreasing. And for the third type, that is very important, as we are increasing the temperature, firstly the solubility is increasing, but reaching at a certain temperature, the solubility decreases with increase in temperature. And in both of these trends, this is the transition. This temperature is the transition in both of these trends. So we know it as transition temperature. If we take perpendicular of this temperature present on this point is transition temperature. Next we have Henry's law. Now Henry's law says that the solubility of gas in liquid is directly proportional to partial pressure of gas present above surface of liquid or solution. Dalton said the mole fraction of gas in solution is proportional to the partial pressure of gas over the solution. Now basically we have to see in this slide, the most important thing is this formula, P is equal to KHX. Now let's see from where this formula obtained. Before that, we have to understand this definition. The solubility of a gas in liquid is directly proportional to partial pressure of gas present above solid or surface of liquid or solution. Suppose here I am having a container which I am having some solution, and above this I am having some gas particles. The pressure they are obtaining on the walls of this container is directly proportional to the solubility of gas. If this pressure is high, the solubility is also high. If the pressure is less, the solubility is less. Therefore, when we buy any of the cold drinks, we we say that we should not open their lid. We should not open their cap for a long time, because all of the gas will spread out into the surroundings and the pressure will very decrease. As the pressure will decrease, the solubility will also decrease, and most of the gas particles will be moving away from that bottle of cold drink, and there will be no taste left out there. It will be just a sweet water. Now let's see how we derive this formula. Suppose I'm having a container. In this I'm having a solution. It is a closed container. Some of the particles of gas are present above this, and they are hitting. They will be constantly hitting, right? Particles of gas are randomly moving particles, right? They move randomly and they will be hitting onto the walls of this container, and the pressure exerted by them is directly proportional to the number of particles, because जितने ज़्यादा यहाँ पर पार्टिकल्स होंगे गैस के, उतना ज़्यादा प्रेशर कंटेन होगा. Now the number of particles depends upon mass, how much mass is present here, and pressure is directly proportional to number of particles, and number of particles are directly proportional to this mass. So indirectly pressure is directly proportional to mass, and here I can write, removing this proportionality sign, I can write mass is equal to Kp. This is the constant. Then at the place of mass I can write mole fraction, that is considered to be very um, a good option at a place of mass. So I can write mole fraction here. Chi is equal to Kp. Now when you will do some shuffling, you will be obtaining that pressure is equal to 1 upon K direct proportion into chi, and this 1 upon K is Henry's constant. This is Henry's constant. We will simply write pressure is equal to Kh into X, and hence in this last slide we had this formula. Hence we obtained this formula in this slide. Here we saw that pressure is directly proportional to chi, that is mole fraction of gas. Therefore we obtained that pressure is directly proportional to solubility and inversely proportional, and Kh, and the solubility is inversely proportional to Kh, that is Henry's constant. Temperature is directly proportional to Kh. Next we have applications of Henry's law. To increase solubility of CO2 in soft drinks and soda water, the bottles is sealed under high pressure. हाई प्रेशर के अंदर उनको सील किया जाता है, so that कि प्रेशर कम ना हो और solubility decrease ना कर जाए. To avoid bends, the tanks used to the scuba divers have their cylinders filled with oxygen and nitrogen. The oxygen when they get underwater, the pressure underwater is higher than the pressure above the ground. When they go underwater, they uh, do scuba diving. The oxygen get into their cells, but the nitrogen is present in their body freely. But when they and hence the pressure is high underwater, therefore its solubility also increases and get into the body. But when they come on the ground, the pressure decreases as compared to that of underwater, and hence the nitrogen gas comes out of their mouths, and a sudden pain they suffer from in their mouth. So to avoid, and this pain is known as vents. So to avoid this, the scuba divers are filled um, diluted helium, as helium is a stable gas. So 11.7% of helium is there, 56.2% of nitrogen, and 32.1% of oxygen. Low blood oxygen causes high altitudes climbers to become weak and unable to think clearly, symptoms of a condition known as anoxia. The climbers at high altitudes, the pressure decreases, the pressure of oxygen decreases, and hence the pressure decreases, and hence the solubility also decreases. So it give them a problem, not anoxia, where they are not able to clearly think about, and some of the symptoms are there in the climbers. Next is Raoult's law in general form. So Raoult's law is for any solution, the partial vapor pressure of each volatile component is in the solution is directly proportional to its mole fraction. When the solute is non-volatile, only the solvent particles are present in vapor phase and contribute to vapor pressure. Let P1 be the vapor pressure of solvent X1, and this chi1 be the its mole fraction. P naught I be its vapor pressure in pure state. Then according to Raoult's law, this is the formula and this is the graph. So now understand Raoult's law in a better way. What Raoult's law says that we have obtained this from Henry's law, right? So the pressure is directly proportional to chi. Now when we remove this proportionality sign, we obtain a constant that is P naught A, that is the partial pressure of component in pure state, and this is the partial pressure after adding the solute. Here in this case also, this is the partial pressure of component, that is the solute. This is solute, this is solvent. A is solvent, B is solute. So P naught B is the P naught B is the partial pressure of component B at pure state, and after making a solution of it, the vapor pressure is PV. Now A solution, the pressure of the total solution comprises from Pa plus Pb. We have obtained this from above, and now we are adding the both and we got this formula right here. Here we have written 1 minus chi b is equal to chi a, because chi b plus chi a is equal to 1. Now here what is chi a, chi b? This is the mole fraction. The graph you obtained from Rolle's law is very important. It says that when the mole fraction of component A is 1, means the mole fraction, the pressure is just because of A, and when the mole fraction for A the mole fraction is 1 and for B the mole fraction is 0, because the total mole fraction they comprise is 1 is equal to 1. So here at this state the mole fraction is for of A is 1 and for B is 0, because means the total pressure of solution is just because of A. And when we move towards the right, what we notice that the pressure of A decreases because the mole fraction of B increases. And when we get back, we see that the pressure of B decreases as we approaches to the mole fraction of A is equal to 1. And the total pressure of the solution is obtained from this line joining the pressure of both. Next we have non-volatile solute and volatile solvent. When we add non-volatile solute to volatile solvent, now what is a volatile solvent? A volatile solvent is a solvent which is able to vaporize, which is having that vaporizing power. Volatile solute decreases the vapor pressure of solvent. According to Rolle's law, the pressure of solution is equal to A, because the solute we added is having no pressure. The solute we added is having no vapor pressure, and hence it decreases the vapor pressure of A also. So the the pressure of the solution is just because of the vapor pressure of A. Now here the pressure of solution is just because of the vapor pressure of A, hence we derive this formula. When we do some shuffling and subtract both of the sides from 1, we obtain this formula, and this is known as relative lowering of vapor pressure of solution. Relative lowering means the vapor pressure initially and then after adding the solute, the vapor pressure, the decrease in vapor pressure, that is relative lowering of vapor pressure. Then we have ideal solution. Now ideal solution and non-ideal solution. Ideal solution are those solution which obeys the Rolle's law, and non-ideal solution are the solution which do not obey the same. For ideal solution, the heat evolved or absorbed during dissolution is 0, but for non-ideal solution, it is a positive deviation and some negative deviation. For positive deviation of non-ideal solution, the heat is absorbed, and for the negative deviation of non-ideal solution, the heat is evolved, means it is a exothermic the solution, and in case of positive it is endothermic. When it comes to when we mix both of them, what is the volume? The total volume change is 0, but here the volume change is increased. The volume change to hoga, that will be increasing. Here the volume will decrease, but here in positive deviation the volume will be, here in this volume will decrease. Now here the AA interaction, when we take, suppose we take two beakers, this one and this one and this one. Here what I have done, I have added A into A, here in this B into B, and here in this A into B. So when it comes to Raoult's law, the AA interaction, BB interaction and AB interaction, three of them are same, they are identical. But when it comes to non-ideal, it is not the same. Positive deviation के case में the AB interaction is weaker than AA interaction or BB interaction. Means there will be more vapors coming out in AB interaction when we add A to B, that is solute to solvent. There will be more vapors coming out. Coming out of vapors means the interaction, the force of attraction is less. When it comes to negative deviation, the AB attraction is more than AA and BB interaction. Means the forces of attraction between the molecules of AB is more than the molecules of AA and BB. Some of the examples are of Raoult of ideal solutions. Some of the examples are benzene, toluene, n-hexane, n-heptane, chlorobenzene, bromobenzene, ethyl bromide plus ethyl iodide, butyl chloride plus n-butyl bromide, acetone, ethanol, acetone, CH2, water plus methanol, water plus ethanol, CCl4, toluene, CCl4 plus CH3, acetone plus benzene, CCl4 plus CH3COH, chlorohexane, cyclohexane, ethanol. When it comes to negative deviation, acetone, aniline, acetone, chloroform, CH3OH, CH3COOH, H2O, HNO3, chloroform plus diethyl ether, water CHCl, acetic acid, pyridine, chloroform, benzene. And with this, we come to end of this presentation. I hope you like it. Thank you. Thank you so much.